I'm Enid, and I will be talking about psychoplastogens, specifically psilocybin, and how it can be a promising treatment for individuals suffering from depression. Depression is one of the leading disability causes worldwide, with a third of the diagnosed individuals being treatment resistant. It is characterized by low mood, lack of interest, and low functionality in daily life. One of the leading hypotheses on the pathophysiology of depression is the monoamine hypothesis, which predicts that the basis of depression is a depletion on the levels of certain neurotransmitters like serotonin, glutamate, and dopamine, for which antidepressants like selective serotonin reuptake inhibitors are prescribed. This theory is now being revised as we take into consideration that SSRIs bind to the receptors upon the first administration, but take between 4 to 6 weeks for the effects to be felt. Another hypothesis is that depression causes neural changes in the brain, like reduced cortical neuron size and neuroplasticity, fewer dendritic spines and synapses in the prefrontal cortex, atrophy of the hippocampus, lower brain-derived neurotrophic factor levels, and functional impairment in the prefrontal cortex. If we take a look at current research, indirect evidence from human studies suggests that neuroplasticity is impaired in major depression disorder. Treatments like psychoplastogens induce regional increases in gray matter volume that are associated with antidepressants response. Wait, psychoplastogens? That's a new word? Well, there is a new classification of 4 compounds that are capable of facilitating structural and functional reorganization of neural circuits to produce positive behavioral effects. And researchers recently introduced the term psychoplastogen from the Greek root psych, which means mind, plast, which means molded, and gen, which means producing, to classify these compounds. Now, to understand how psychoplastogens work, let me quickly review what is neuroplasticity. Neuroplasticity is the brain's ability to change and adapt to its dynamic environment. This can be at a functional level, like when the brain suffers from damage due to a stroke and is able to move functions from damaged areas to undamaged areas. Or it can be at a structural level, which is the actual change of its physical structure as we learn or form new memories. Neuroplasticity also can be observed at a cellular level, like when we talk about neurite growth, changes in dendritic density and synaptic strength, or at a molecular level with changes in the signaling pathways, which include BDNF and tropomyosin receptor kinase B pathways, and which are activated by a calcium ion influx through depolarization, or N-methyl-D aspartate, the NMDA receptor activation. It sounds very technical right now, but I promise all these hard to pronounce concepts will make psychoplastogens easier to understand. To be classified as a psychoplastogen, a compound must produce measurable changes in plasticity, like the ones we covered before, changes in neurite growth, dendritic spine density, synapse number, etc. Accomplish these changes within a short period of time, usually between 24 to 72 hours, following a single administration, unlike traditional antidepressants that take several doses and weeks for the effects to be felt. Now, because their impact on neuroplasticity facilitates change in the neural circuits, they should produce relatively long-lasting changes in behavior, even beyond the sharp effect of the drug. Right now, there are several compounds classified as psychoplastogens, with ketamine being the first one researchers identified. Another psychoplastogens include the muscarinic receptor antagonist scopolamine, entactogens like MDMA, and serotonergic psychedelics like LSD, DMT, and psilocybin. Now, ketamine and psychedelics target different receptors. Ketamine targets the NMDA receptor, while psychedelics target serotonergic 2A receptors, but they have similar effects on structural plasticity as by activating mammalian target of rapamycin, which is a protein that have been related to plasticity. This might be important because ketamine is known to be addictive, while many classical psychedelics are not. To explain a little bit more how psychoplastogens work, I will use psilocybin as an example on how it can be used to treat individuals affected by depression. So the body processes the psilocybin and converts it to psilocin, which binds with the serotonin receptors called 2A. This increases the activity in the visual cortex, which translates to altered perception or even kaleidoscopic fractal images. Decreases the activity in the default mode network, and that is why subjects report a loss of ego, and increases connectivity among different regions on the brain. In a 2021 study, Chow and colleagues demonstrated that a single dose of psilocybin evokes growth of dendritic spines in the middle frontal cortex of the mouse. The persistence of neural modifications is notable and may relate to the compound's therapeutic effects for at least two reasons. First, depression is associated with a loss of synapses in the frontal cortex, and restoring the number of neural connections may correct that deficit, providing a biological mechanism to alleviate the symptoms of depression. Second, as we mentioned when discussing neuroplasticity, structural remodeling is necessary for learning and facilitates the storage of lifelong memories. So, psilocybin-induced neuroplasticity could prime the brain for integrating new psychological experiences. The results indicate that the underlying structural trace in the brain is enduring and can be observed a long time after the initial drug exposure. There is increasing evidence that psychedelic agents, like psilocybin, may induce rapid synaptic plasticity, and that this plasticity may be a key mechanism by which they can exert long-term antidepressant effects. However, it is important to note that plasticity is not by itself an inherently antidepressant action. Actually, several mental illnesses like depression, anxiety, and PTSD can themselves be caused or exacerbated by maladaptive forms of plasticity. If we take trauma, for example, we can see how a single event linked to mechanisms of plasticity can cause long-term detrimental effects on the brain and behavior. But serotonergic psychedelics may well be the opposite. A pharmacologically induced state of altered consciousness in which experiences are integrated due to heightened mechanisms of synaptic plasticity. The goal now is identifying factors that can predict how patients will respond to psychedelic-assisted therapy, which will be important for maximizing efficacy and reducing adverse events. For example, patients who exhibit apprehension, preoccupation, or baseline attachment avoidance appear to be more likely to have challenging experiences following an administration of a psychedelic drug. At the same time, the ability to selectively modulate neural circuits using small molecule psychoplastogens opens up new horizons in neuropsychiatry focused on healing pathological neural circuitry rather than masking disease symptoms. That's all I have for now. Thanks for watching.